with Chapter 9, Stoichiometry. Awesome word. One of my favorite words of all time. Because it should be anyway. What is it? So brace yourself for stoichiometry. Sure. Forget for not bringing mine. All right, so what is stoichiometry? Up at the top of your note sheet, it has this information. Basically, it's a nice little sentence. It's kind of the definition. So right next to where it says Chapter 9 Stoichiometry, it's got a little quotation there. It's mass relationships between reactants and products in a chemical reaction. So it's already written down for you. You don't have to worry about writing that down. But it sounds pretty interesting. When you look at a chemical equation, a chemical reaction, remember we have to balance it. You have to have the same number of atoms on both sides of the equation. So if we looked at the mass relationship between reactants and products, it's going to be the same. It's the same mass that we start with, it's the same mass that we end with. So there's always going to be relationships there. So however much mass of one of the reactants I have has to be related to the masses of the products that are going to be produced. So there's always going to be a relationship there. It's basically, this is our chemistry recipe in that chemical equation. So if we needed to double the recipe, we would know if we had double the mass of one chemical, we would know we would get double the mass of what our other chemicals. Either the ones we need to react with or the chemicals we're going to produce. If we needed to cut it in half or 1/4, we would know that relationship. That relationship is very obvious and very useful to us. So as condescending Wonka would say, tell me more about this. This sounds awesome. It's powerful. Oh, thank you. Yeah. So, a couple more things that you don't need to write this down, but this is a quote. I guess the person who said it is he's a famous chemistry person anyway. It says that stoichiometry uses the facts of chemical reactions and that law of conservation of mass. Same mass on the reactants, same mass on the products, to be able to make those powerful predictions about how much chemicals are needed to react with and how much chemicals are going to be produced. So basically what we're going to be doing is using those powerful abilities to be able to make those conversions and find information from other information. That's what science is always about. Trying to be able to make those really powerful predictions about something and then being able to see them come true. That's always a nice thing. So really, stoichiometry is just going to be unit conversions. So we're combining a bunch of things from the past. Chemical formulas, finding molar masses, using T-charts to do conversions, and of course, what we just got done with, those chemical equations and looking at those relationships. All right, so this is a little bit of review, especially for those of you that missed out the review on Monday because we got out a little early. So I want to make sure that we get this stuff written down. So that is available on your note sheet. Down at the bottom is moles. And we can convert mass to moles or moles to mass. And our other one that we can work with pretty easily is particles. So in order to get between mass and moles, the piece of information we need is the molar mass. So I'm going to write that alongside those arrows there somewhere. The molar mass. So that's going to the periodic table and adding up all the atoms in that chemical formula. That would be the mass in grams of 1 mole of that material. When we are going to use that information in a conversion, if we're going to go from moles to mass, that means that in our T-chart, the molar mass is going to go on top. So when something is on top in a T-chart, what do we do with it? Multiply or divide? Multiply when it's on top. It's a multiplication. So if we're going the other way, from mass to moles, that would mean that the molar mass is going to be in the bottom part of the T-chart. So that would be division. Division. We have the same relationship when we're going from moles and particles as well. Except this time we're not going to be using the periodic table. We use Avogadro's number, 6.02 times 10 to the 23rd. But if we're going to use it in a T-chart, it'd be the same deal. If we're trying to go from moles to particles, it would mean that Avogadro's number is going to be up on top of our T-chart, so we would be multiplying. And of course, going the opposite way from particles to moles, Avogadro's number would be the bottom of our T-chart, so we would be dividing. So that's a quick little review. So, in order to do these conversions, in order to use stoichiometry, we really need just two main things. First one, periodic table for molar masses. When we're going to convert from moles to grams or from grams to moles, that's one big thing we need to have. The other thing is our balanced chemical equation, because that gives us mole relationships between chemicals. Those are our two big things that we need. So one does not simply do stoichiometry without getting moles involved. We need to convert to moles. Moles will be our key. All right, so here's our first chemical equation. It's not balanced for you on your sheet. You want to make sure you balance that thing, because a balanced chemical equation is key. Just the equation isn't going to be too helpful. It needs to be balanced. So 4 aluminum reacting with 3 oxygen, and we get 2 aluminum oxide. So we have to look at how we're going to interpret those coefficients. How do we interpret those numbers, 4, 3, and 2? There's 2 ways. First way is small scale. Small scale way, if we look at that equation, we are kind of like are reading this equation in terms of our minds in terms of chemistry. 4 aluminums, well, it's 4 atoms of aluminum reacting with 3 molecules of oxygen, forming 2, that's a weird word, formula units of aluminum oxide. So notice that those are the things, atoms, molecules, these things are particles. So small scale, we're looking at particles. That makes sense. These particles, atoms and molecules and formula units and electrons and everything, they're tiny. All you need is particles. We need to write all that other stuff. Try to make this easier. But we want to look at it large scale too, because remember, these are representing numbers of things, 4 atoms. Well, mole is a number 2, a really big number, but it's still a number. So we can look at this as 4 moles of aluminum reacting with 3 moles of oxygen molecules, producing 2 moles of aluminum oxide. Nothing but moles in there. Large scale looks at moles. So we can use this chemical equation, those numbers, to represent moles of those chemicals, those particular substances. Stoichiometry is going to be using that large scale mole representation. So these are going to be the relationships we're going to use for stoichiometry problems. The coefficient numbers are what we're going to need. That's the relationship. 4 aluminum with 3 oxygen. That's the one relationship that we can use. So here's our mole ratios. So some of you on Monday got to kind of talk about this a little bit. Those of you that didn't, you really want to pay attention. So it's the same equation. Still aluminum reacting with oxygen, making aluminum oxide. We can write ratios 2 ways. There's that little colon way, or it's kind of the more mathematical. They're both mathematical. So if we look at a relationship between aluminum and oxygen, it's 4 to 3. 4 aluminums reacts with 3 oxygens. We could look at it the other way. Oxygen compared to aluminum, which is just reverse it. 3 compared to 4. 3 to 4. But when we're using them in a t-chart, we're going to be using them kind of like as a fraction representation. So it can be written two different ways. My relationship of aluminum to oxygen could be 4 moles of aluminum over 3 moles of oxygen. Or I could flip that around, have 3 moles of oxygen on top, 4 moles of aluminum on top, or on the bottom. Depends on what we're going to be using them for, which one you would pick. Pick either that one or that one. So that's just one of the possible combinations. We also have, I'll be kind of careful with this one when you're writing it. This is aluminum to aluminum oxide. So that goes to down and to the left there. Aluminum to aluminum oxide is 4 to 2. Don't worry about the oxygen not being involved. It's okay. We just want to know the relationship between aluminum and aluminum oxide. So focus on those two. 4 to 2. Bless you.
Thank you.
So again, we can write that with the little colon in there, or we can write that as fractions, which is the way we would represent them with a t-chart. One of those compounds on top, one of them on the bottom, with their relationship numbers from the balanced equation. So 4 moles of aluminum over 2 moles of aluminum oxide, or 2 moles of aluminum oxide over 4 moles of aluminum. Yes, Mason?
Where do you get like the 4?
Where do I get the 4 from? Right there.
Oh, up
Yeah.
at the top.
All of these mole numbers are going to come from our balanced coefficients in the equation. It'll make a little bit more sense when we start working with some of the problems. Because where people get confused and they want to use those numbers a lot more than what they want to. You only need to use it once. All right, our last relationship is between oxygen and aluminum oxide. So that's going to be a 3 to 2 relationship. 3 oxygens get me 2 aluminum oxides. So in our t-charts, we would write it as 3 over 2 or 2 over 3. So let's take a look at the kinds of problems that we would run into in doing stoichiometry. There's really just 3 main types. And really we're going to mainly focus in on just 2 of the types. Every once in a while I might sprinkle them in the other ones. First one is a mole-mole relationship. Mole-mole problem. That's where we're going to start off with an amount of moles of one of those chemicals in the equation. And we want to know the relationship, how many of the moles of one of those other chemicals, either one of the other reactants or the products. How many moles are we going to get from that? So our starting unit's moles. Our final unit will be moles. The difference is the starting unit moles will be of one chemical, one formula, and our final one will be a different one. Either one of the other reactants or one of the products. Or one of the other products. Mass mole problems, we're going to start with either moles or grams, and we're going to end with either moles or grams. But if we're starting with moles, our answer will be in gram. If we were to start with grams, our final unit would be moles. Makes sense. Grams are what we use to measure our mass in. So one of them is going to be grams, the other one's going to be moles. And our last one, mass problems, which are probably the most useful for us because we measure everything in the lab using a balance, so we get mass a lot. Grams and grams. Yeah, oops. I knew there was something that was kind of funky. right, so let's dig in. Take a look at a mole-mole problem. We've got a different equation here, different chemicals, but look, it looks almost the exact same as the aluminum one. Aluminum is a 3+ charge, oxygen's a 2-. In this case, iron is going to be a 3+, and oxygen is still a 2-. So it looks exactly the same. Wow, crazy. But we got two questions here. How many moles of oxygen are needed to react with 0.42 moles of iron? And then how many moles of iron 3 oxide, or product, will be formed? So, we need a T-chart. Start off, you draw a T-chart on your note sheet there. We always start these problems with the information they give us. They're giving us 0.42 moles. And it's always a good idea to kind of keep track of what chemical you're talking about. So 0.42 moles of Fe, iron. So that will be our starting point in our T-chart. 0.42 moles of iron. Now I want to get from one chemical to another one. I want to know how many moles of oxygen needs to be present to react with that many moles of iron. So I'm going to use that mole relationship, those mole ratios from our balanced equation. So I'm going to take that 4 moles that's represented in that equation and bring that down so that my units of moles of iron cancel out. And since the chemical I'm interested in is oxygen, I'm going to go back to my chemical equation and look at what's the mole relationship. It's a 4-to-3 relationship. So it's 4-3. So 3 moles of oxygen is going to go on top. The only time you're going to see numbers that potentially are other than 1 are here when you do the mole-to-mole switching of your chemicals from one to the other one. Because that's where you're going to get these guys. So I look at my units, do my dimensional analysis. My moles of iron are going to cancel out. Now what we need is a calculator. So your calculator will be a very handy tool to be using for a lot of these problems. So I take my 0.42, times it by 3, and divide by 4. Answer comes out to 0.32 moles. It actually has like another decimal. I think it's 0.315, but we got to do sig figs too. So started with 2 sig figs, we ended with 2 sig figs. I think now's a good time for Science Cat to give us a good message. So, Science Cat. Science Cat loves stoichiometry because moles are his favorite snack. Yeah, different kind of mole. Oh, it's totally pleasant. So let's take a look at the second part of that question. We want to know how many moles of our product would we get then. So we're just figuring out the 2 reactants, how much was needed. So I'm still starting with the same amount. If I start off with 0.42 moles of iron, how many moles of my product can I produce? So I start off my T-chart the exact same way, because I have the exact same information that I'm starting with. But this time I got a different mole ratio, different mole relationship that I'm interested in. It's still going to be 4 moles of iron going down on the bottom, because I want moles of iron to cancel out. But my other chemical this time is Fe2O3, so the top number is going to be 2. 2 moles of Fe2O3. Get those numbers from my balanced equation. You're still hanging on that. Now what you can do, you can mathematically, you can kind of see this one. 2 and 4. What can I do with that if they're in the one's on top, one's on the bottom? 2 and 4. I'm going to reduce that down, right? 1 over 2. If you don't reduce it down, that's okay. You're going to get the same math. Take 0.42 times 2. But basically, it's 0.42 divided by 2. My answer should be 0.21 moles Fe2O3. And that makes sense. However much iron I have, I'm going to get half of that produced. It's 4-to-2 ratio. Works out perfectly fine. Does that mean I lost some iron along the way? Well, no, because this is 4 iron, but over here 2 Fe2O3s has my 4 iron in it. It's kind of like a recipe. If I need 4 cups of this, and I need 2 cups of this, that's how it's going to work. All right, let's take a look at the next one. Mass mole problems. You don't have this equation balanced, but there are the numbers for you. This is the burning combustion of propane. So that was one of the questions on the test. So if you remember, 534 is a number sticking in your head. You probably got that one right. So our mole ratios, there's more mole ratios now because we got an extra chemical. Last equations only had 3 things. 2 reactants and 1 product. Now we've got 2 reactants, 2 products. So I've got a 1-to-5, 1-to-3, 1-to-4, a 5-to-3, a 5-to-4, and a 3-to-4 ratio. But here's the question. We want to know how many grams of carbon dioxide are going to be formed if we're going to burn off 3.48 moles of propane, C3H8. Guess what? Still a T-chart. Still a T-chart. What are we going to start with?
3.48.
3.48. You guys got it. Moles of C3H8. Now we're starting with moles here, so I want to get rid of moles right away. So I'm going to bring my mole ratio from a balanced equation down in here. So there's nothing written in front of C3H8, so that means that it's 1. 1 mole of C3H8 will react with 5 moles of oxygen and produce 3 moles of carbon dioxide, 4 moles of water. Up on top, yes, I want 3 moles of CO2 because that's the chemical I'm interested in. If it had asked how many grams of water would form, what would we put up there? 4 moles of H2O. Not 4 moles of CO2. But in this case, we want to know carbon dioxide, so we put 3 moles of CO2 on the top. We cancel out our units looking at dimensional analysis here. We've got moles of carbon dioxide. That's not what our answer wants, though. It wanted grams. Uh-oh. Ruh-roh, Reggie. We need to add another step to our T-chart. Here's where it gets tricky. What am I going to do to get to grams? You can look at your number sheet up near the top of it. What would I need to do in order to get that information? Where would I go? Well, there's like a big giant thing that gave me information that I could use to figure molar mass. Yeah, periodic table. There it is. Now remember, everything off of the periodic table is related to 1 mole of it. Don't put a 3 here. That's the biggest mistake I see students make, is that they'll, for some reason, always think, oh, I got to use the equation up here to get my numbers. It's only one spot that gets used. That's it. If you're using your numbers off of your balanced equation 3 or 4 times in a stoichiometry problem, you're getting the wrong answer. 1 mole of CO2. When I go to the periodic table, I add 1 carbon and 2 oxygens. That adds up to 44.01 grams. That's the molar mass of carbon dioxide. Cancel out moles of carbon dioxide now because my T-chart says I can do that. So now I take 3.48 times 3 times 44.01. My bottom numbers are all 1, so I don't care about those guys because divided by 1 doesn't change nothing. That's a double negative. That's up to 459 grams of carbon dioxide.
So like, are these ones always gonna be like 3 steps?
These ones are 3 steps.
But like the first one is always gonna be 2 steps?
Correct.
Yeah.
You got it. You will see that pattern in a little bit. Guess what the last one's going to be?
4.
All right, we'll do one more mass mole problem. You should still have enough room, hopefully left enough room along the side there to be able to do a second one.
Advanced chemistry.
This is getting nitty gritty of chemistry. We want to know how many moles of water will be produced if we take 238.6 grams of oxygen and burn that with our propane. How many moles of water would we get? Guess what? It's a T-chart. Remember? It's all unit conversions. That's all we're going to be doing. What am I starting with? 238.6 grams of oxygen, O2. I need to get that to moles though. We have to get to moles. It's the only way we can switch from one chemical to the other one is by using those mole ratio relationships in the balance equation. So you got to get to moles. So we use our molar mass off the periodic table. Oxygen gas is 2 oxygen atoms combined, so it's not 16, it's 32. And our grams of oxygen then cancel out, so woohoo. We got one more step to go though, because we still haven't gotten to the chemical that we're interested in. We haven't gotten to water yet. So we need another step. In this step, now I'm going to use my mole ratios here. So I'm going to have 5 moles of oxygen, and that connects with 4 moles of water. That's my mole ratio from my balanced equation. Only use those numbers once in these problems. But the good news is now I'm done because I have the unit that I want. I wanted moles of water. So break out your handy dandy calculator. Put 238.6 in your calculator, divided by 32, times by 4, divide by 5. And with our rules of sig figs, that comes to 5.956 moles of water. The question is, how do you measure that in the lab? Our balances don't have little settings that say moles, unfortunately. You'd have to program the heck out of those things for every different chemical that you have. So here's what we need to do. Mass problems, mass problems. We're going to power through these and then maybe get a little bit of time to talk about your next assignment a little bit. So because these are a little bit longer, we split these up on the note sheet. So we're going to be doing 2 problems. So there's a little bit more room for you to be able to do these. Our balanced equation is up here. N2 plus 3H2 gives us 2 NH3s. So in terms of moles, that's 1 mole of nitrogen. Reacts with 3 moles of hydrogen gas and gives us 2 moles of ammonia. So we want to know how many mole or how many grams mass we can measure of ammonia are we going to get if we take 147.2 grams of nitrogen. The key is we need to get to moles, because these numbers allow us to be able to switch from one chemical to the other one, but only by using the mole ratio relationship here. So we're starting with grams of nitrogen. We need to get the grams of nitrogen to moles. Where do we go to get that?
The periodic table.
The periodic table. So we have 2 nitrogens, because it's N2 gas. So 14.01 plus 14.01 is 28.02. That is equal to 1 mole of nitrogen. Always when you're adding up off the periodic table, remember, in your mind. That is what is equal to 1 mole of it. Should always be your other number in that part of your T-chart. So grams of nitrogen will cancel out. Now that I have moles, my next step would be to do my mole-mole ratio. So nitrogen has nothing in front of it, so that means that it's a 1 down here again. Just happens to be coincidence that they're both 1s. But up on top, the number I'm going to want to have here is from my balanced equation. That would be 2 moles of ammonia. So moles of nitrogen cancel. Now I have to add one more step. This is a 4-step problem because I need to get to grams of ammonia. So if I go to the periodic table to add that up, that's going to be 1 mole of NH3. So 1 nitrogen plus 3 hydrogens is 17.04. All of my units cancel out except for the unit that I want, which is grams of ammonia. So it's calculator time. Put 147.2 divided by 28.02 times 2 times 17.04. It's 179.0 grams of ammonia. So using my recipe up here, 147.2 grams of nitrogen will get me 179 grams of cookies. I mean ammonia. Different recipe. Our last problem. In this equation, in this reaction, we've produced 0.285 grams of ammonia. We could then figure out, kind of going backwards a little bit, how much hydrogen was needed in order to make that happen. Kind of like a forensic scientist. The crime was we produced ammonia. Got to go back. Who created that? Who did it? So we start off with what's given to us in the problem. 0.285 grams of ammonia. We need to get to moles so we can use our mole-to-mole ratio from the equation. So that means I got to have 1 mole of ammonia off of the periodic table. Still the same amount, 17.04 grams. Once I've made that convert, once I've got to that point, I can now use my mole-mole ratio, which in this case is a 2 to 3 ratio, 2 to 3. The 2 ammonia goes down in the bottom, 3 hydrogens on top, 3 moles of hydrogen over 2 moles of ammonia. That way my units cancel. Last step then is to do my calculation to get my mass of hydrogen. So going to the periodic table means 1 mole of hydrogen, add 2 atoms of hydrogen together because it's H2, 2.02. And then it's calculator time. So 0.285 divided by 17.04. Multiply by 3, it's on top, and divide by 2. And then times 2.02. I've got 3 sig figs that I started with, so my answer should have 3 sig figs. That's only 3 sig figs. 0.0507 grams of hydrogen. Okay, so as kind of a visual, kind of like those of you that are more visual learners, let's take a look at this. This is not on your note sheet. But if I need to get from one chemical to the other chemical, there's this big, I don't know, this is a river or a big divide, big like canyon or something. There's only one bridge. Moles gets you to moles. It's the only way you can do that. You may know particles, you may know mass. But they can only get you to moles of that same chemical, X. We're in the country of X over here, or state of X. Particles can't get you over here right away, directly. There's no bridge there. So the only way is to get to moles first. Then we use our mole-mole ratio from our balanced equation to get to our other side. And then if we needed to, we can figure out how many molecules or atoms are present, or what mass is there, or needs to be there. It's the only way it's going to work. So again, one does not simply do stoichiometry without converting to moles. You've got to get to moles. So let's take a look at a stoichiometry algorithm. Flip that over to the other side. Oh, that's algorithm.
Who's Al Gore?
Al Gore, he's like, he ran for president a while ago. He used to be vice president. Now he's an environmentalist. So if you flip it over, you've got a little kind of a little algorithm that kind of will help show you how to do some of these stoichiometry problems. It's kind of like you kind of plug this stuff in and solve as you go. So notice that this is kind of set up for mass problems. It's got 4 steps to it. What you start with, a conversion to get 2 moles. Then you can do your mole-mole ratio from your balanced equation. And then if need be, you can convert that to grams or particles if you needed to. So, the given unit, given number and unit, that's what you start with. So in some problems it might be moles, like 0.48 moles. Or it might be grams. It might be particles. We're starting with 3.2 times 10 to the 22nd power atoms of something. But what's that big X there? Well, the big X is the formula of your starting compound. So whatever chemical it is that you have information about is what you're going to be your X. Y is the chemical you want to get information about from that information you have about X. The known number in unit would be what goes down here. So if your unit up here is grams, you're going to have grams in that next spot. They say it's a known number because you can go to the periodic table and get that information. Or you go to your brain and you get 6.022 times 10 to the 23rd. If it happens to be particles. This is atoms and atoms. The little n sub y thing, that's kind of the confusing part for me. That's the coefficient of that chemical y in your balanced equation. So nx would be your mole number from your balanced equation for X. So those two numbers are our mole ratios from that balanced equation. In the last spot, you've got that known number and desired unit. That's what you want to get to. So if you wanted to get to mass, it would be your molar mass for whatever that chemical is, chemical Y's molar mass off the periodic table. So if you're starting with moles, you can skip step 2. Because step 2 is really, you're converting to get to moles. Well, if you're already in moles, you don't need to convert to moles. You're already there. So you can skip step 2. Yeah.
But you're going to be okay.
And, like if you had a mole-mole problem, you're starting with moles, you want to end with moles. If your desired unit is moles, you skip the last step, step 4. Because getting here will get you to moles. So that's only a 2-step problem. That makes sense, Mason? Yeah. So you can see it's a 2-step problem, or it's a 3-step problem, or it's a 4-step problem.
Oh yeah.
Oh yeah. Oh yeah.
I never said no. I never asked you to do it. Did I did.
They really made it seem that it's not fun back.
Let's not have slow
Alright, so let's take a look at some of these problems. Let's give you a chance to get kind of a couple of them done.
I am now waking up at 6 o'clock.
Let's take a look at number 3. Let's go, people, please. So exciting to get a worksheet, I know. Let's do at least a couple of them. Number 3 should be pretty easy because I've already given you that equation. It's already been balanced for you. It's in your notes, on your note sheet. It's propane. Propane reacting with oxygen to produce carbon dioxide and water. We're starting this off with 0.38 moles of C3H8. So I think you guys know how to do that. What's going to be my number and my unit on the top of my T-chart here for this problem?
1 mole.
1 mole CH3.
1 mole of CH3 on top?
Yes.
No, it's already there.
Oh, we'll do the bottom first? All right, we'll do the bottom first. 1 mole C3H8. And on top would be? Got to figure that out. But like I said, I just gave that to you in the note
Oh,
sheet.
it's 3 now.
Not 3.
44.
one
Grams.
4. 5. Why is it 5?
3 moles of CO2.
It's the balanced equation. Once we're at moles, we need to convert from moles to moles. We need that mole ratio. So yes, we would use 1 mole of C3H8. In this problem, this is a mole-mole problem. It says right alongside there, it says the first 4 are just using our mole ratios. So we're skipping step 2 and step 4 here. So we go right to that mole-mole ratio from off the balanced equation. So it's 5, 3, 4 after our C3H8. So it's 1 to 5 is my mole ratio. And because I'm starting with propane, the 1 goes on the bottom and 5 goes on top. So this is it. That would be your calculation. We've got time to do one more. Let's do one of the ones down at the bottom. These are going to be mass problems. So they're going to take all 4 steps to do these ones.
All right.
Let's stick with the number 3, except this time we're going to put a 1 in front of it. Number 13, find the mass of benzene required to produce 2.66 times 10 to the 24th power molecules of carbon dioxide gas from the reaction described by the following equation. It's already balanced for you. There's your good news. So I'm going to start off my T-chart.
Yes, Nate.
Yes, Nate.
Yes.
Oh yeah, Nate.
2.66. times 10 to the 24th. And let's see, what is that? That's molecules of CO2, right? Whew. That's a long start to the T-chart.
I can't even see it.
I know you can't. I'm going to put it up there because I left that stoichiometry chart up there. 2.66 times 10 to the 24th molecules of CO2. I need to get that to moles. Always have to be getting to moles. If I'm not starting with moles, got to get there. So what goes on the top up here? 1 mole of what? It's X. Same chemical.
CO2.
CO2. What goes in the bottom has to be a known number of some sort with that same unit that was up on top up here. So I need molecules down here. What number would go there? 44.01. Nope. 44.01 is grams. 6.022. Avogadro's number.
Sure I may. So we'll come back and eat.
Here we go. All right, next step.
How long do you have them?
According to that algorithm up there. What would I put up on top? 2 moles. C6H6. And at the bottom would be 12 moles CO2. Moles of CO2 are gone. My last step. 1 mole of C6H6.
I don't know what is that equal?
That's a good question. Carbon is 12.01. There's 6 of them. 78.12. About. Pretty close to that. So if I added up 6 carbons and 6 hydrogens off the periodic table, that would be my answer. 78.12. Those cancel out, and I'm left with my answer. So it's just a matter of putting numbers into my calculator. Be careful with Avogadro's number. Remember, if you do not have that EE button, you need to use parentheses when you're dividing by Avogadro's number, or you're going to get a messed up answer.